Thank you. So I will talk about the description of two-dimensional conformal field theory correlators in terms of three-dimensional topological field theory. It's based on work with Jürgen Fuchs and Christoph Schweiger, quite a long series of papers. I will try to talk about these three topics roughly in the 3 lectures, so I'll probably not manage to stick to time. So I want to describe chiral conformal field theory via TFT, the full conformal field theory, and then I want to talk about sort of some more general bits and pieces one can put into this. And to explain a little bit what this means, I maybe start with an example, and then I can put at properties, can point at properties of the example, and then you will see maybe what these mean. And my running example will be the two-dimensional Ising conformal field theory. And so that's a conformal field theory which has central charge half. And I'm hoping that most people in their own setting have seen that theory before. And I want to talk about a specific correlator in there, and to do that I want to introduce 2 functions which I call f plus minus, which depend on a complex number z, and these are z to the minus 1/8, 1 minus z to the minus 1/8, and then I get 1 plus minus square root of 1 minus z. All of this to the half 2. So these are my 2 functions. So clearly I don't want z to be 0 or 1. So that lives in the complex plane less 0, 1. Good. And now I want to look at the correlator of the Ising model for the correlators of the Ising model, spin field, so Ising CFT spin field, which I call sigma. So that, if you know, is the one which has conformal weight 1/16, 1/16. And I want to write the 2, 3, and 4 point function of this. So what's the 2 point function? That's say sigma of z. I don't want to write it like this, sigma of w. So in conformal field theory, 2 and 3 point function are always entirely fixed by conformal symmetry up to an overall number. And so I choose to normalize my field so that here I get just a modulus of z to the minus 1/4. Then the 3 point function, let's say do sigma of 1, sigma of z, sigma of 0. This is easy to write. It's fixed by conformal invariance up to a number, and that number is 0. So this is just 0. And the 4 point function is the one where I need my f here. So I place my 4 points at infinity, 1, z, and 0. One has to say a little bit what one means by putting a field at infinity. I'll do that later. But let's just live with it for now. And so I say this 4 point function in the Ising conformal field theory is given by taking f plus of z squared plus f minus of z squared. So let's stare at this a little bit. So what properties do we observe? So one property we observe is that these functions are actually single valued in z. Right, so it's clear here, less clear here, but in your head, you can do, you can do the analytic continuation of z around 0, right? So that picks up a phase, but that phase goes away because I'm taking the absolute value here. More interesting is if in your head you do the analytic continuation of z around 1, right? Because if you do that here, you go to the other branch of the square root, so it changes sign. So if you walk around, if you take 1 around, if you take z around 1, then you get a phase from here, but you also switch between the 2 solutions. So luckily, this function here, this particular combination is still single valued, right? Because the phase is eaten by the absolute value, and the fact that you walk between these two solutions is okay because I've just added them together like this. Okay, so we get single valued functions. There's another property, which is factorization, of which you can see a shadow here, which is that if you take z close to 0, you can convince yourself that the 4-point function, the leading behavior, is the product of two-point functions. So that's not the complete factorization property, but it's a consequence of it. And you also notice that somehow all of these correlators I'm writing, which are correlators of the Ising conformal field theory, are built out of holomorphic functions, out of bilinear combinations of holomorphic functions where you take one holomorphic and one anti-holomorphic. So it has these holomorphic building blocks. Right, and so these holomorphic building blocks are what is called conformal blocks. And you see that somehow this correlator is built out of these functions. And so the studying these functions, that's the job of chiral conformal field theory. It is concerned with the holomorphic building blocks of the final correlation functions of the CFT. The study of these correlation functions, which are single valued and satisfy factorization and so on, that's what full CFT does. It tries to come up with solutions for these correlators. And so I want to discuss these in turn. I'll start with the chiral one, which is concerned with these holomorphic functions, and then we go to the full theory and so on. So that's a bit the plan. And I want to, before we go there, I want to make one more comment about these correlators. So let's sort of make a motto, is that is the geometry and the decorations. Like the geometry is the complex plane with these specific choices of points where I insert my fields. The decorations are what field I actually insert. Up to the correct notion of isomorphism between these objects should determine the correlator. Of a conformal field theory, or more precisely of a full conformal field theory. Right, so again, in this example, if I would have maybe four fields in the complex plane, that's my complex plane, and I put a field, maybe this is the spin field again at all of these points, then to this, my prescription to assign correlator should assign a number, right? And so in particular, if I now sort of do some deformation of this geometric situation where I maybe exchange these two fields, then the output of the theory, because then the configuration after this process is the same, has to be the same number, right? So that's what I mean by single value. It can't be any monotomies. The configuration determines the number. And in the type of CFTs I will look at, so what's the geometric information? So I would have maybe a complex structure on a surface. I would have an orientation. I have these insertion points. These points actually get local coordinates. That's something I'll talk about later. Then they are labeled by some fields that I'll also talk about later. So some vectors in some vector space. And depending on what you want to do, you may also want to pick an actual metric. So that would be the geometric information. And if you have two surfaces equipped with this data and you find the structure preserving isomorphism, then that's not allowed to change the value of the correlator. Okay. So that's a bit the setting. And of course, you can vary this, right? You can say, well, maybe I want to equip my surface with a spin structure. Then again, the rules change a little bit. You could say maybe my field theory has parity, then maybe you need to actually have to introduce some ordering on your fields, which then which sort of gives you signs if you change the ordering because of parity and so on. So there are variations of this, but the one I will talk about is this one, which you could call, if you want, you could call this oriented CFT. Okay, does that make sense? Are there any questions or comments?
What would be the non-oriented CFT? Just not considering orientation.
And you could also do this, right? So you just drop the orientation, then you could have like a CFT on a Klein bottle with some complex structure on it that you can build, but I will not. More questions or comments? Okay. So then the question I want to address in the first part is, so we have an interpretation for this function there. It's a correlator of the 2D easing CFT. But we can ask, say, what about these functions f plus minus of z? Can we think of these as correlators in some sense? So, one thing that certainly doesn't work is just, again, say we have maybe P1 or C with infinity, and we have points infinity, say 0, z1 infinity. So it's not true that to this configuration, this would be a valid correlator, because if I continue z around 1, the answer changes, right? So that doesn't work. This kind of geometry, just giving the marked points, doesn't remember enough information to say which precise function I'm talking about. So then you can think, what do I have to do to deal with this? And one thing you could try and think about as well, maybe I just need to include more structure in the geometry here on the surface. Maybe I have to sort of remember some lines which pass between them, so that now it becomes visible that I have done this monodromy. That's something one can try. That's not the thing I want to try. What I want to do is the following. I want to think of a three-dimensional geometry which has a two-dimensional boundary, and on the boundary it has a complex structure and an orientation. So I want to think of a three-ball B3. Then on its boundary, I put a complex structure. So I write P1 for the Riemann sphere. And then I again get my marked points on the boundary. So I don't know, 0, z1, infinity. And now at these points, I want to have a ribbon graph which extends into the three manifold, maybe something like this. And so I want to ask, can I assign correlators to such configuration? So can I assign a number to this, which only depends on the geometry I've shown here, and not on anything else. And we'll do a little example to see how this might work with this function f plus minus in a moment. And then to see where I'm heading with this in lecture 2, I then want to argue that to recover that precise function over there, the specific geometry I should choose is S2 times an interval. So that's a three ball with a smaller three ball removed here. And again, on the boundary, I put a complex structure, and the specific graph I put into this looks like this. And I want to in the first lecture and probably bits of the second lecture introduce how we can evaluate such graphs to numbers, and then show that if you do this for the easing CFT, you get that function. Okay. So that's what I wanted to say about holomorphic factorization. So it's the idea that you take correlators in conformal field theory, and you understand that they are products of holomorphic and anti-holomorphic functions, and you first develop a theory for the holomorphic functions. Other questions or comments? Yeah.
Sorry, just to make sure I understand correctly. So the F plus and F minus, those specify the chiral, anti-chiral parts of the theory. The F plus is multi-value, but they come together to form some single value thing
Yeah.
Okay.
So F plus and F minus are both holomorphic, right? But I'm saying I want to sort of have a way to say, if I draw such a picture, what kind of specific combination of F plus and F minus you are looking at. You do that in an example.
Sorry, you're trying to say that from full CFT, you want to reconstruct chiral optimization?
I see. So my ploy to sort of get to where I want to go has already confused you. It's not a good sign. So I wanted to say, why do I want to talk about chiral CFT in the first place? And I want to say, look at this correlator. It is clearly built out of holomorphic functions. And so I want to have develop a theory of how to deal with these holomorphic functions and then be able to formulate in terms of TFT how to combine holomorphic and anti-holomorphic functions in a single value way. So I don't want to start with full and reconstruct the chiral. I want to start with the chiral and build full. And I wanted to motivate why that may be a good idea.
So you're not going to talk about vertex separators?
No. Should I? No.
No.
Beautiful. I could, but I will need more time. So I'll use a number of black boxes here and vertex operator algebras and how they are used to construct actual space of conformal blocks concretely is one of these black boxes. Okay. What? I agree it's all beautiful. Vertex algebra is beautiful, conformal blocks beautiful, but I can't explain about it. More comments or questions? Right. Okay, so then we go on. 1.2. 1.2 is 3D TFT with conformal boundaries. And there are bits of this lecture which are math and bits of this lecture which are not math. And this is a bit of a lecture which is not yet math. So I mark the bits which are not math with an X, and I will put a green tick if bits of it are actual math, so that you can distinguish what you can actually prove and what is more of a wish list. So bits of this section will be more of a wish list. Okay. So what's my input? My input is, I start vertex operator algebra. It's a vertex operator algebra, which I want to be rational or strongly rational, I think would be the correct jargon here. And I want it to be simple. So I will not talk about logarithmic theories here. That is, so this formalism works to some extent already for logarithmic theories, but I want to focus on the simplest case, which is rational theories. For example, we could take the Virasoro VOA at C equals a half. By this I mean the irreducible quotient. And so this, for applying the theory to this example, should reproduce the equals here. I want to keep my function a bit. So let's see. Okay, so then from this input, I first of all get a modular fusion category, and I will not explain how. So I look at representations of V, and we've seen in a number of talks that this category comes with a lot of structure, and in my settings, that's a modular fusion category. And so that also appeared, started to appear in Martha's talk. So these are categories which are braided. The braiding is non-degenerate, and by fusion, I mean that it's actually semi-simple. So the underlying tensor categories are semi-simple. Good. So we have we get this, and what does it look like in our example? So the leasing example, you would get that C is the leasing modular fusion category, and it has simple objects, which would be the three irreducible representations of that VOA. So representation one is labeled, say, by one tensor unit. So that's just the VOA itself. And there's R sigma and R epsilon. And I will, in this example, work with heavily overloaded notation. So rather than writing representation one, I just write one. This one I will call sigma, and that one I call epsilon. So these are my three simple objects in this category. But they have sitting, underlying, because I'm starting from this VOA. These are actual infinite dimensional representations of the VOA. So for example, what does R1 look like? So that would be the span. There's some ground state, which I've in heavy physics notation have such a ket vector here. And then there's a state where you generate the other states by acting with Virasoro modes. But as opposed to what we saw in the lectures on Liouville theory, you don't get a basis by acting with all by just these generators indexed by Young tableaus, because they're not all linearly independent. Right? For example, L-1, 0 is already missing here. Here I don't have to write L-3 because the same as this one. So there are additional relations in these rational series, but still it's true that if you act in the Virasoro example with all Virasoro modes, you just generate certainly the module. And so maybe I didn't want to call this 0, maybe I want to call it the ground state 1. Because it's the ground state of the module 1, but it's still true that if I act with the conformal generator L0 on 1, I get 0. This one here also has a ground state, I call it sigma, and if I act with L0 on sigma, I get sigma, and so on. Good. So I said this easing category, so if you just talk about the easing modular fusion category, then you wouldn't know this. This you only know if you also know that it's representations of some VOA. So this is a braided monoidal category, so it in particular has a tensor product. And so for example, if I take a sigma, and I'm using this shorthand notation, and I tensor it with sigma, then that's the same as taking 1 isomorphic to 1 plus epsilon. That's an example of such a tensor product. Okay. I want to keep my functions, so I will erase this. Other questions or comments? So then, out of such a modular fusion category by the Restiken-Drive construction, you get a 3-dimensional topological field theory. The Restiken-Drive construction. And what does it give us? It gives us a 3D topological field theory, which goes from some category of Bordisms in dimensions 3 and 2, which contain ribbon graphs decorated by C into vector spaces. And it's extended in some way, which I will not discuss much, but we have seen bits of this in Marco's talk this morning. So what Marco is doing is he sort of adds another layer here, but I will just use the top 2 layers. So 2-dimensional parts for objects, surfaces for objects, and 3-dimensional parts, Bordisms as morphisms. Then the extension was this with Lagrangian subspaces and so on, which he talked about. That happens here as well, but I will also not use it much. And these theories should come out if you use the theory which Marco presented this morning. You plug in this semi-simple input and you restrict to the top 2 layers. So that is the relation. So this, again, I should say that's actually math. So ticks here. That's math. That is math. And so that's a symmetric monoidal functor by definition. Good. So you get a topological field theory from this data. You also get something which is called the space of conformal blocks. So let me say a little bit what that is. So let's say we take a surface with some oriented surface with a complex structure. So this little C indicates that I've got a complex structure. So let's say that's my sigma C, some torus. And I've got marked points. P1, P2, Pn, finitely many marked points. for each of these marked points, I give a local coordinate system. So I have some neighborhood here, some holomorphic map phi1 injective, which maps that to some neighborhood of 0 on the complex plane. So P1, so the point around which I'm giving the coordinate, always gets mapped to 0. Right, and then you have the same for P2 and so on up to Pn. Good, and so if I give you this, so let's give all of this data some name. So I don't know, I call this sigma underline C. So sigma is the surface and it has this extra data. So I give it an extra underline. So that is sigma C together with this collection of marked points and local coordinates. And out of this, I get something called the conformal block function. Okay, so conformal block functor. So for those who've been in Gui's talk, that you did see that quite extensively. So in this situation, we have n marked points. So we get a functor from representations of v to the n, so n copies of my VOA into vector spaces. And I will call this conformal blocks for this marked surface sigma C. And it takes such a representation and just introduce some notation, maps it to conformal blocks for this surface marked with R. I'd say a little bit more what that is, but not much. And so this is a subspace of linear maps from R to C. Okay, so if you, so it took me a while to get used to thinking of V to the N modules altogether. So I would have usually written it in the way that I just take a tensor product of modules for individual copies of V. So if my R is of the form R1 tensor yada tensor Rn, where each of these R's is a representation of one copy of V, then this would get mapped to some space of conformal blocks which are assigned to a, right? So then we would say we have our marked point P1 with some coordinate and P2 and so on. And then I would label, think of this point P1 as labeled by representation R1, point P2 as labeled by representation R2 of my VOA and so on. And then because I've got an underlying VOA, I can get out of this a space of linear functions from R1 tensor over C, R2, and so on into the complex numbers. So this is what is called the space of co-invariance with respect to the V action, which I'm not going to define for you. I'm just saying that because all of these are representations of the VOA, to such a configuration, I can get a space of co-invariance, which is a subspace out of multilinear maps from R1 times R2 and so on to C, or linear maps from just a tensor product to C. Right, and then it is sometimes useful to say, well, why do I restrict myself to such pure tensors here? Let's just take generic representations. That's sometimes a useful tool to have. Okay, so what's more, because our V is so nice, it's sort of rational, simple. These vector spaces, subspaces of these, so these first of all finite dimensional subspaces of this infinite dimensional space of linear maps, and they assemble into a bundle. So we have this bundle of conformal blocks, which eats a surface and the representation, and it lives over the moduli space of Riemann surfaces of some genus with some number of marked points. And at the marked points, you need some extra tangent decorations, which is sometimes included by putting a tilde over this. So this, in a way, takes care of the fact that I had to choose these local coordinates. Right, so this is a finite length bundle. And I will not explain how. And it comes with a projectively flat connection. And also this is half. And so why is that useful to have this connection? Because it means if you know the conformal block at one point for your moduli space, then you can use the connection to transport it to another point up to an overall coefficient, because it depends by this projective flatness, it does depend a little bit on the path, namely up to a number. Okay, so for example, in my easing example, right, so we had these three representations, and I claim that if I look at the conformal blocks, so if I look at conformal blocks over the moduli space of genus 0 with 4 marked points, and I label the 4 marked points by this representation per sigma, all of them, then this space of conformal blocks is two-dimensional. Okay, so that's the span of some. Well, at each point, it's a span of two functions. Let me write it like this. So it's a span of two things. It's two-dimensional over each point, but they're not global sections. So maybe the notation is not so good. But it's certainly of rank 2. Actually, because I'm in genus 0, it's slightly better the situation. The connection is actually flat, so I can transport without ambiguity. And if I evaluate say this F plus and F minus at on the surface, so on P1, so genus 0, I'll write it as C with infinity. And I've got my 4 marked points, which were infinity, 1, Z, and 0. And I have to give local coordinates. So I write little local coordinate functions, and I'll say what they are. For the phi 0 here. Then I'm claiming this, so just to give an example, then these conformal blocks, so that F plus is now a linear function on this tensor product. But if I evaluate it just on the generating state, on the ground state, on this state sigma, then that is what these functions are. Okay. And I should maybe say, we don't really use this much, but so what's this local coordinate? It would send zeta to 1 over zeta, and these coordinates here, they send zeta to just shifting the point, zeta minus z. Just for completeness, to give an example of what these may look like. Okay, so, but that's now an example of such a conformal block, which I evaluated. Yeah.
So in terms of the F plus minus, what is the projectivity of the flat connection?
So because I'm in genus 0, it's actually flat.
Okay.
And the connection acts by analytic continuation in this variable. And then we see that it's not single valued because if I rotate around,
okay. But the project, so in a higher genus, the project.
In a higher genus, there would be a projectivity which was depends on the central charge of the theory, and I'm struggling with the details of that too. So I expose that more by asking you more questions on it. But here it's actually flat. Are there more questions or comments? Okay, so now I would like to combine these two things. So having these conformal blocks which depend on a complex structure, and having this 3D TFT, which sort of also works on 3 manifolds, but there on the surfaces is a topological theory, so there's no complex structure, and I want to pack this together. So I clean the board, but let me first say what I want to do. I want to combine these. Combine into a 3D TFT with some formal boundaries. That's a bit which is not mass. I think it can be made into mass, but it has not been made into a precise mathematical theory. But I find it very useful to organize in your head what is going on and where the conditions come from. Let's say that. Okay, so what would we like to have? We would like to have a theory which works on 3 manifolds. Maybe 3 manifold M, which can have a non-empty boundary, the M. On the boundary, I want to have a complex structure, and in fact, I want the structure of one of these things I erased. So I want the structure of one of these complex surfaces with marked points, so marked points and local coordinates. Then at each of the marked points, I want there to start. I want to start a ribbon. And then inside the 3 manifold, I can have one of the usual ribbon graphs, which one is used to from Stick-Interal theory. So, you know, there can be ribbons and coupons. Maybe there's some internal topology inside the 3 manifold here. And so pictures like this one. I want each of these marked points. So that's my marked point P1. It has maybe some local coordinate phi1. And I also want to fix some representation R1. Then here I would fix a representation R2 and R3. Assign to this. Right, and then these ribbons, because I'm using the same category, so these are representations of my BOA, but there are also objects in this category C out of which I constructed the TFT. And these objects also label the ribbons inside the ribbon graph. So these ribbons are also labeled R1, R2, R3. And these coupons, they are morphisms in the category then. So this F in this example would be in the home space of the category C from, what is it, R2 tensor R1 in my example. 3. Okay. Let me.
Since they are ribbons, it probably matters how to glue them to the boundary, right. And they each use a tangent vector.
So good. Tangent vectors. So I've got my local coordinate, and so I can just sort of take the pre-image of the unit vector in the at 0 in the complex plane. So I get for free from my local coordinate, I get little tangent vectors here, and these are actually ribbons or framed lines, and so I have to sort of glue them in the standard way. I will not talk about this much because again, get more technical stuff, but that's where you get that. Yeah. The more comments or questions. So let me call the collection of let me call the collection of this data an underline. And now what I would like is to this data, I want to again assign a number. So that's my sort of chiral CFT correlator, if you want. So it now is not determined only by the 2 manifold, but also by the way it is attached to a 3 manifold with embedded ribbon graph. But to this, I want to assign a number, which only depends on this geometric and labeling data here. Okay. And again, technical point, because I don't know how to deal with the projective correction properly, I want to normalize these. If I take this empty ribbon graph, so forget the marked points and the graph, I just normalize that. Okay. So I am saying it. So that's a useful picture to have in mind, that we can assign a number to this data. And let's look at one example. Again, in the easing case. So I take so as a surface, I take P1, which is C with infinity. So I'm drawing it as a section of the complex plane, and I want to think of this as a boundary of the 3 wall, B3, 3 wall, and its boundary I want to give. I want to explicitly parameterize it by C with infinity. And I want to have 2 marked points, one at 0 and one at Z. Or I do like this. Okay, and the local coordinates are the one induced by the fact that they already sit in the complex plane. I want to label each. Sorry, I forgot the vectors. No, that will make sense here. So as I've mistake, as I've written it here, it doesn't yet make sense. I also have to pick specific vectors. So once I pick specific vectors in here, then I get a number. Otherwise, I just get a linear function. Okay, and so here I attach the representation R sigma to the 2 of these, and I want to pick the specific vector, which is the ground state, so the lowest conformal weight state. And I want to make sense of the statement that sort of the correlation function of this picture, 3-manifold with conformal boundary, is the holomorphic, but not globally defined function Z to the minus 2h sigma, where h sigma is the conformal weight of h sigma. Okay, so I want to try and make sense of this state. So here the problem is that I would have to choose a branch cut of that function, and I'm saying as Z sits here on the positive real axis, well, that makes sense, and this is my assignment. But now I ask, what happens if I take this point and I continue it around here, right? Because that's a holomorphic function. I've got no freedom. What happens if I do this continuation? What happens is that this goes to e to the 2 pi I minus 2h sigma times z to the minus 2h sigma. This is my analytic continuation. So I have to give the graph. So in here, that sits now my ribbon graph. Let's do a graph like this one. So I've got sigma, sigma, and here's some f. And I sort of choose the f such that I get coefficient 1 here. Now, if I do this process of moving the point z around the point 0, then the new graph I end up with looks as follows. So again, my 2 points are inserted at 0 in the same z, but now the graph inside has changed. So there's my f. And now we have to do, I can't do this live in my head. So I just draw the graph and you tell me if I did that right. So I say that what comes out of it is this graph here. Yes. So if I do the process of moving that around here to come back to the same location, then the graph inside my 3-manifold. Right? So now for this claim that I can assign a number to such a configuration to make sense, it better be true that to this configuration I would assign this number, right? Otherwise that's not consistent. So let's see if that works. So here, this is a topological field theory. So I can do TFT computations with ribbon graphs. So I can look at this bit and do a TFT computation here and see what I get. So I try to reduce this configuration to that by just doing a computation in here. So that's a string diagram computation. So for the sake of this argument, I will read string diagrams from top to bottom. So the string diagram here is I've got my F, and then I've got these two gradings, and these are both labeled by sigma. And now, well, maybe that's an exercise. The exercise is to show that you can turn this, if you compute what this diagram is, you find that it is a ribbon twist on the ribbon labeled on the sigma ribbon to the -2 times the untwisted picture. Okay, so I'm allowed to replace the picture I've encircled here by this picture, provided that I multiply everything by the phase theta sigma to the -2. And what is this? So theta sigma, in the way it comes out of the representation theory of the VOA, is e to the 2 pi I times h sigma. Right? And so that's precisely this phase here. Right? So in this one example calculation, this did indeed make sense. So if I do this continuation on the analytic function side, I get this answer. And on the side of the conformal boundary attached to a 3D theory, I get this answer, and the two answers agree. So that's not surprising, because that is how, if one tracks back where the category C and its tensor product and its braiding comes from, that's precisely how that is set up for this to work.
Is this like somehow trying to get like a chiral like half of the correlation functions or something like this? Like...
Right. But I'm trying to have the point of view that I can think of the chiral. So what is chiral half? If you just look at conformal blocks, and these are multi-valued functions on the moduli space, and I want to get rid of this multi-valuedness. I want to say, if I point at a configuration, I can get a well-defined number out of that. And the way to get rid of the multi-valuedness, or one way to do this, is to attach it to a 3-manifold and remember the sort of some ribbon graph which extends to the interior. So this picture allows you to select a specific conformal block in the space of blocks. That's another way to think of it.
And where these vectors come?
These
I mean, the sigma, you didn't choose any vectors. Yeah, this one, yeah. For your computation, you didn't choose.
Right. So I'm saying that if I do these, if I choose the lowest weight vector sigma in here, then the answer look like this. That's sort of my hat out of which I pull the answer. I could put other states in this representation, and then this function would look different. So I could put an L-1 sigma here, then I get a different function. So this, I'm not telling you how you get this function. I'm not computing that for you.
Oh, okay. So I just thought that the sigmas are representations. So on the right hand side.
Some
Right.
highest weight vectors
Are there
of that
two?
representations.
This is my heavily overloaded notation.
No.
So there's R sigma, which is the representation of the VOA, which I just labeled by sigma. It's one of the symbols, but it takes so long to write R sigma. So I write sigma. Unfortunately, the lowest conformal weight state in here is also called sigma. And there'll be more sigmas later. So this sigma is the highest weight state, and this R sigma is why I call this line sigma. Maybe less confusing to call all these R sigma, because then that's the object in the category. Does that have anything to do with your question?
Yes, but this TQT computation does depend on vectors. Yeah, it depends.
Yeah, it does. It does depend on the choice of this vector. But if I put this function changes, right? But that statement will still remain true. So if I get a different function, but it'll have the same monodromy. Again, it's not clear. I just want to do one example. I'm not presenting it as a finished theory, but this is how you compute the braiding on this category out of conformal blocks. That's what you do.
in comparing to like the bit of TQFT that we know, what makes this not math? I mean, what part of this?
What makes this not math that I claim that there is a well-defined assignment which takes such a configuration, gives you a complex number.
So in this case, you're just actually using the already constructed VOA information that you already have to get the C to the -2 H6. You're not computing it in any way, other than from the category you already have.
Well, and the VOA, right? So if I just know the category, I can't tell you what these functions are. So that come out of knowing what the conformal blocks for the VOA are. Can you ask the question again with more words or more?
I'm just making sure that in this case, it's because we already have computed the conformal blocks and we're just saying that's what that would have to be.
So I want to present this as a way of thinking of specific conformal blocks. You can think of a specific conformal blocks is the proposal by taking a 3-manifold with a complex boundary and it points at a specific block. And so it makes sense to evaluate it on vectors and then you get a number. More questions or comments?
So how really physical it is? Are they like easy case? Can you really make sense of this as an assignment? Does it exist as an assignment?
Let's see cross here, right?
The cross is in general for the general claim.
And in well,
Yeah,
the problem is
maybe
the
there are
same.
examples where it is.
So I think if one puts together existing ingredients, one can probably make this work. I'm just saying it hasn't been written down as a coherent theory. There's actually a question if there are any probabilists left. So what worked very well so what is very beautiful in this Liouville examples is that you have this formalization of the path integral, and it allows you to point at a surface with metric and insertions, and you get a number out of this. Then you can check that this assignment satisfies the consistency conditions one would have postulated in conformal field theory. So that is very beautiful. And one can now ask, does that object here also have a probabilistic representation in some way, right? So where your geometry is slightly more complicated because you have this attached 3-manifold, but maybe there's still a probabilistic description which produces for you a number, and then one can check that it satisfies the required properties. So that would also be very pretty.
Are there like required axioms here as well? Like, can't you maybe?
Yeah, again, I pointed my X. So it would be, right, so so if you want to develop, so I want to use this as intuition on how I translate between state spaces of the TFT and correlators in conformal field theory later. But if you want to turn this into a fully developed theory, you indeed would now have to develop first a Bordism category, which has conformal boundaries, which are not gluing boundaries, and then you have to cut across these and see that things compose correctly. So there's I'm not sure how easy it is to make that rigorous.
If graph is empty, can I put empty graph?
Yeah, I put the empty graph.
What would be function? You put full correlator?
If I put the empty graph, I sort of want to normalize it to 1. And the reason why I want to do this is that that I only have this projective connection. And so I don't see in my head a consistent way to get the partition functions because it's only projective connection. But that is just.
But it will depend on the insertion points.
So the empty graph, the empty graph means the mark points are labeled by the VOA, right? So then you're just evaluating the conformal block with V insertions.
I see.
Also, there can be no graph, but still mark points.
Well, but the mark points are labeled by the so no graph in the sense that
trivial labels will be that will count as an empty graph.
Yeah. Well, yeah.
So if labels are not tensor units, you have to connect them somehow, right?
Okay. Time left. Yeah.
For managing time, there will be no lunch tickets,
Okay.
but there will be lunch served in the room upstairs, which is called the cathedral. This lunch is delayed.
Oh.
So lunch is not ready at 12:30. So I suggest that we give Ingo 10 more minutes so that we do not have to wait.
Oh, and I'm not delaying. I'm making you enjoy the time until. Good, thank you. Any more questions or comments? So
Sorry, if I have a space of conformal blocks and I choose certain graphs, is it clear which graph I take, or I should look at the monodromy properties and so on? Like you explained?
well, so claim is such a picture points at a specific conformal block. But how? I'm not telling you. But you know, so here's an example. Just one more example. So again, I do this P1 boundary. So that's the 2-sphere, and I've got my 3-ball here. And now I want to have insertions at 0, Z, 1, and again, infinity. And then if I do a graph which looks like this, so again, I mean, my easy example for all of this is labeled by R sigma. And I always, in each of these, pick the lowest weight state. Then I can look at a picture like this, graph like this, and then I can connect here with either the tensor unit or with epsilon, because the fusion rule says sigma tensor sigma is 1 or epsilon. And so I decorate this ribbon by either the tensor unit or by epsilon. And all other ribbons are decorated by epsilon. And here I make some choice of, which I'm not specifying you what it is, of element in the home space, which is non-zero. And then I say that, so if, you know, yeah, so I say that if I put 1 here, then this gives me my F plus of that. And if I put, so for 1, maybe I call this alpha for alpha is 1. And it gives me F minus of that for alpha is epsilon, for example. So that would be another assignment. You can see that you can think of this as composing intertwining operators, right? So that is one way of thinking.
Or specific couplings, the vertices.
So you say what?
Also to choose couplings at the vertices.
Right. So I'm not telling you what these are. I'm choosing sort of a non-zero F and G here, and there is a choice so that comes out like this. Is what I'm saying.
So if you do the monodromy also.
Yes, and now there's a good exercise. It gets a little star because it's not maybe so easy. Is you do this monodromy, and you check that it switches these blocks with the correct phase in front of them. Go.
Oh.
Go to the blackboard.
So that's an exercise. I encourage you to try it and get confused. But I claim that.
And if you reverse some arrows?
Right. So there's so in the easing case, these are all self-dual, right? But I want, so if I have a, so technically, if my ribbon approaches this point in this direction, I should really put the dual contragradient rule, but I don't have to worry about it in the easing example. So I say that later, but for the easing example, I wanted to skip this. Okay. That's exercise. Okay. So now I want to use this picture that we can maybe assign of 3-dimensional correlators to the 3D TFTs with conformal boundaries. And I want to use this as a way to think about comparing different notions of modular functors. Again, I will not give the mathematical definition of modular functor. That's best done using the 2-categorical language which Marco started to present. So it will take a bit of time to do this. But I want to give the intuitive picture in terms of these manifolds with conformal boundary. So what's the idea? So where are we heading? Maybe let's state that again. So we want to go from the description of chiral conformal field theory, which in a way is what I've done there. Right, so it gives me chiral, it's a way of specifying specific conformal blocks, so that you can think of as chiral conformal field theory. And I want to go from there to full conformal field theory, where I don't need to remember the attached three-manifold. And I want to ask in which way can I combine my conformal blocks into something which is consistent two-dimensional theory. And I want to answer this question by using only 3D TFT, not 3D TFT with conformal boundaries. So I have to somehow get rid of the conformal boundary in a controlled way. And the idea to do this so that we can phrase our problem entirely within 3D TFT is to just cut off the conformal boundary. Cut off conformal boundary. Again, this is, so there'll be, at some point, so in the next lecture, I don't have to make red crosses anymore, because then we'll only talk about topological field theory, but in the transition, there are bits which are not fully mathematically established. That's one of them. So what's the idea? So we have one of these graphs. So we have maybe our conformal boundary. And we have some three-manifold here. Then so maybe there's some ribbon graph. So that selects a specific conformal block if you want. So to this, I can, if I put all the labels, I can assign a number. And now what I want to do is I want to take the conformal boundary. Let's see. And I want to cut off a neighborhood. I want just to cut off boundary times the interval. I want to cut that out of the manifold. I want to cut off. So it's 3 dimensions. I don't need the complex structure anymore. Times some interval. Okay. So what does that give me? So inside here, I've got a 3D TFT, so I can cut along surfaces, and then I get 2 3-manifolds which I can glue together. And so I expect so we expect a picture like this one. So there's a conformal boundary out here. So that's some, so you can see. Then I've got this 3-manifold, which is sigma, the underlying manifold without the complex structure times an interval. It has a complex structure on this boundary, but on the other boundary, it doesn't. Right, so here it's just a topological boundary, but it's parametrized by sigma. So this boundary is parametrized. It's a gluing boundary for the TFT, maybe in this case parametrized by the identity. And then using this gluing, I glue back the graph. I can glue back the graph I've cut off, which like this. So here, this boundary is then also parametrized, maybe with some ISO by sigma. And so I've decomposed this 3-manifold into something with a gluing boundary and an honest boardism in the boardism category of 3D TFT. So if this theory were to make sense, what would we expect this to give? So it would, inside here, this is the topological gluing boundary. So the TFT assigns to it a vector space, the state space on this boundary. So let's say I've got the Richtig-Imperative theory, Z for the modular fusion category C. I evaluate it on this specific surface. It gives me some vector space. So that's the vector space the TFT assigns to that surface. Times, and well, these are all labeled by representations, R1, R2, R3 of the VOA. So R1 tensor tensor Rn. The complex numbers. That's what we expect from this, right? Because if we glue this back, well, then we just get a function from here to the complex numbers. But we can also think of this as moving this to the other side, right? Once I point at the vector in the state space, then I get a linear function from the tensor product to C. So I want to think of this as something which goes into R1 tensor dual functions from here to C. And specifically, I wanted to land in the space of conformal blocks for the surface sigma C and these R's. So let's stare at this a little bit. So I want to give an interpretation to this picture. It has a conformal and a topological boundary. The conformal boundary is unparameterized, but it has a conformal structure. The topological boundary is parameterized by my surface. I claim this gives me a linear map from the state space that TFT assigns to the surface to the space of conformal blocks. Right, again, this is a wish list. This is not math, but it is so to understand what are the conditions I need to compare the conformal blocks on the outer surface, which has a conformal structure, and just the states in my TFT. I claim that picture is helpful. And probably next time I will want to give, so what I want to say is that this map compares two modular functors, one you get out of the TFT and one you get out of the VOA, and so it has to be compatible with mapping class group action and gluing, and I want to express it using this intuitive picture. And after I've done that, we will forget all about conformal boundaries, and we can use that to translate all questions into just TFT. So that's what will happen, I think, on Wednesday. Okay, yeah, sorry. So there's already a question.
So your left-hand side doesn't depend on any conformal structure. So, and right, it has a difference. So how, where it come from? So how can it
possibly work, right? And okay, so I give an example next time where we do one calculation to see how these ingredients play together. But the idea is that if you, as you vary the complex structure here, you're sort of moving along a path in the moduli space of complex structures, and you use then your projectively flat connection to transport the conformal block, right? So it means that for each choice of complex structure, you point at a specific conformal block, and for different choices of your complex structure, well, the two different conformal block spaces are connected by a path in moduli space, and you can transport. But of course, a priori, you have to worry that this transport should not depend on the path. Right, and that's where the compatibility of the mapping class group action here and here come into play. I'll try and say that next.
Okay, I think we already smoothly transitioned to the discussion session, but let's thank Ingo and let's ask for more questions.
So part of your wish list will that this map will be an isomorphism, right? Okay.
There'll be three wishes: one, iso; two, compatible with mapping class group; three, compatible with group.
What do you expect this thickened surface to be? A topological manifold, a manifold with conformal structure, or?
So let's see what it is. So inside here, it's just a smooth three manifold, no metric, just oriented. On the boundary, outer boundary, I have a conformal structure, complex structure if you want, it's oriented. And on the inner boundary, I do not, but it's parameterized by the concrete underlying surface. And so what we will do, what I try to do next time is that I sort of do an element of the mapping class group on the complex side that's sort of moving a closed path in moduli space. We will see how that translates into acting with the corresponding mapping class group element on the other side.
So why do the labels live outside of the topological bit? I would think that I have some topological theory which admits labels on the boundary and that they would kind of live inside of the Z sub C sigma, whatever.
Can you say that more loudly?
So the labels that you have for your manifold on the topological side, they live kind of outside of, so you have the ZC sigma times the objects.
Right. So the labels here are just, again, these representation labels, but no elements in the representation. That's just out.
Right.
Because we are getting this linear map. Right? So,
I'll ask you after.
Okay, then before closing the morning session, let me say that tomorrow at 9:45, there is a welcome by the director of Institut Pascal. So we start at 9:45, not at 10 o'clock as today. And let's thank Ingo and Marco for their nice lectures.